Hello, everybody. We're very excited to be here today. Also because I almost didn't make it. I was stuck in Dubai for like 32 hours on the way over. We're going to talk about the firmware modification attack and remote debugger we developed for the Siemens S7 PLCs. And before we begin, I just want to say thank you to Professor Eli Biam, Dr. Sarah Bitan, and Alon Donkner for the joint work. And also a very special thank you to Dr. Marina Krotofil and Dr. Ali Abbasi for the dedicated mentorship. So I'm Ron Semmel.
I'm Eyal Semmel.
As you can see, we're brothers. We've been collaborating for almost 25 years together. I'm a software engineer at Microsoft and also a security researcher at the Technion.
And I'm a security researcher at the Technion.
So we're not the first to research Siemens PLCs. Many people have done it before us. So our first topic will focus on previous research so we can build a strong foundation for the rest of our talk. We're going to talk about the runtime manipulation of Siemens S7 PLC firmware and how we leveraged it to develop a remote debugger for the Siemens S7 PLCs. And finally, a video demonstration and conclusions. So can anybody here imagine life without water, transportation, food, or even our Amazon shipments? So today, our lives' necessities are made accessible via highly automated industrial control systems. And these systems include wastewater treatment plants that purify our drinking water. Our traffic is managed using complex signaling systems. Even our food is grown using automatic irrigation systems. And our online purchases are managed in automated warehouses. And these smart control systems include mass integration of IoT devices, extensive cloud communication, and smart automation. But all these cool features come with a lot of risks. And cyber attacks on critical infrastructure can be devastating. For example, the Triton malware was specifically designed to disable safety systems, which can prevent industrial accidents. It was first discovered in a Saudi petrochemical plant. Just think how deadly this kind of attack can be. And due to these consequences, we have a great responsibility in securing these systems. Now, a PLC is a very rugged computer used in industrial automation, and it's the core component of an industrial control system. It reads input data from field devices, such as sensors, and then it triggers outputs based on pre-programmed code. So you can kind of think of it as a bridge between the virtual and the physical world. Now, a little off topic here, we're from Israel. It's very hot over there, kind of like here. And you can just imagine yourselves like walking down the streets. In the summer, 100% humidity, everybody's always sweating, it's sticky. So we love ice cream. But the problem is, Eyal here would always finish my ice cream growing up. So at a very early age, we understood that ice cream factories are critical infrastructure that must be protected. And here's an example of how an industrial control system would work in an ice cream factory. So the factory has these industrial tubs, which the ice cream is prepared in. And each tub is connected to a PLC. And the PLC gathers data from the tub during runtime, such as its temperature. And then, based on that data, it can change the tub's behavior. For example, it can tell it to stop. Additionally, the statuses of the tubs can be viewed remotely in an engineering workstation, and the PLC's custom control logic can be updated remotely from it. And here's some very important and relevant previous research regarding Siemens PLCs. The Doors of Turin team discovered a special access feature to the Siemens S7 1200 PLC's bootloader, which was exposed via the UART interface. And using this special access feature, they were able to upload firmware directly to the firmware flash, and thus bypass all the integrity checks. The Rogue 7 team discovered that all the Siemens S7 PLCs of the same model share a single hard-coded private key used for communication. And this motivated Team 82 at Clarity to actually discover these keys. And once they did, Siemens updated their communication protocol, TLS. And Colin Fink and Tom Dorman showed that even a decade after Stuxnet and all the security improvements that came with it, that the Siemens S7 PLCs are still in attacker's heaven. And we'll show you why. And because PLCs are the main target of attacks on critical infrastructure, we focused on the largest PLC vendor, which is Siemens. And also because they invest the most in securing their products. More specifically, we focused on the Siemens ET200SP Open Controller, which is a next generation PLC. It was specifically designed to match the growing needs of Industry 4.0, and it serves as a platform for modern software applications. It overwent some serious design changes which opened it up to new attack vectors and methods, and it also runs on standard hardware. In this case, it runs on Intel Atom CPU with 4 cores, and it's one of the leading PLCs in the market. It also includes a built-in software PLC, which is called the S7-1500 software controller. And basically, it's a software application that simulates the functionality of a traditional hardware PLC. And just to be concise throughout the talk, we'll call it the SWCPU. Now, for years, Siemens has kept the firmware of their S7 PLCs a secret. And they also invested a lot of resources in protecting their intellectual property. For example, the Siemens S7-1200 PLC self-destructs if a watchdog discovers that one of the cores was halted via the JTAG interface. And this was first discovered by Thomas Weber in 2019 and reproduced by Ali Abbasi in 2020. Additionally, the software PLC we talked about earlier is encrypted on the Open Controller. And this was discovered by the SOF7 team in 2022. Now, we introduced a revolution in the research of these Siemens S7 PLCs. And for the first time in S7 PLC history, we removed from these PLCs their many layers of obscurity. We introduced a powerful remote tool to dynamically analyze their firmware, and we can easily expose secrets that have been kept secret for years. And as a byproduct of all this, we managed to install persistent malware on the PLC, which can communicate with the remote command and control server. So at the lowest level of this PLC, we have a bare metal hypervisor, and it launches 2 guest operating systems. The first operating system is the software PLC, and its main responsibility is to communicate with the field devices, like the industrial tub in our example. The second operating system is the Windows embedded operating system, and its main responsibility is to communicate with the engineering workstation and cloud platform. And naturally, these 2 operating systems communicate between each other using inter-OS communication. And the isolation between these 2 operating systems provided by the virtualization is a very important security layer. And this is because if the Windows operating system is compromised, we still want the field devices controlled by the software PLC to remain safe. The boot process is fairly simple of this open controller. We have a BIOS which loads the grub bootloader, which loads VMM first stage. And it's the first part of the hypervisor. It's mainly responsible for setting different configurations. VMM first stage loads VMM second stage, which acts as the brains of the hypervisor. It loads the Windows embedded operating system and also decrypts the encrypted software PLC and loads it into memory. Now, our research continues where the SOF7 research ended, and that's Black Hat USA 22. Remember that in the previous slide, we showed you that the hypervisor decrypts the encrypted software PLC and loads it into memory? The SOF7 team managed to extract the plaintext software PLC file. So now we could start studying its assembly code. And additionally, but also very, very surprisingly, they discovered that the hypervisor and software PLC firmware files can be easily accessed from the Windows file system. Which means that these 2 operating systems aren't that isolated if the files of one can be accessed from the other. And by simply dragging and dropping, we can easily replace these files. As a side note, replacing the hypervisor is easier than the software PLC, but we'll touch up on that later. For now, just a video demonstration of how we replace the hypervisor. So here on the left, we can see the modified hypervisor. And on the right, we can see the original one. And as you can see, by simply dragging and dropping and giving admin privileges, we can easily replace the original hypervisor. And when the PLC reboots, the modified hypervisor will be the one that's loaded. And they leverage this new capability to crash debug the hypervisor. And what do I mean by this? So for example, how could they know who calls this function? They started by overriding an instruction in the hypervisor with the int3 command. So in our case, they overrode the first instruction of the function with int3. They then replaced the original hypervisor with the modified version using the drag and drop method we showed you in the previous slide. And finally, when int3 executes, a crash dump will be produced. And this is kind of a hidden feature of this PLC. If we look at the top, we see the PLC, and on the bottom, we see the crash dump. And if we zoom into the crash dump, we can see the hypervisors, registers, and stack. If we look at the top of the stack, we can see the function's return address. And that's how they discovered who calls this function. Now, before we continue to the rest of the talk, just a quick recap. The Debug7 research enabled us to study the software PLC's assembly code, easily modify the hypervisor via the Windows file system, and crash debug the hypervisor. And going forward, we'll be presenting our contributions. And what will we show you? So we'll show you how a bad actor or nation state could persistently install malware on the PLC, how to set up communication with a remote C2 server, how to remotely and dynamically inject commands to the software PLC, and how to exfiltrate data from it. And if you're a researcher like us, we'll show you how to read runtime information from the software PLC, how to get a better understanding of the code flow. And finally, this will all expedite your research process exponentially. Now, our research process was kind of like robbing a bank because it had kind of many steps and challenges. So we took a gaming approach into doing it. And that's why we developed a game called Bank Heist, and we'll be playing it throughout the talk. So I hope you enjoy it. And now we can actually start to talk about the runtime manipulation of the software PLC, which leads us to the first level of our game, which is to gather intelligence about the bank, or in our case, research the firmware. But we encountered a slight bump in the road. So remember that earlier we showed you that the Debug7 team was able to easily modify the hypervisor and run it. We wanted to do the same to the software PLC. But the problem was that the software PLC is encrypted on the open controller. And the Debug7 team didn't discover the decryption method or key. So after we would modify the plaintext software PLC, we didn't know how to re-encrypt it to match the hypervisor's decryptor. And if we were to just replace the encrypted software PLC with the plaintext version, it should just crash, right? So what we did is we started by reverse engineering the code in the hypervisor that loads the software PLC. And we discovered that the hypervisor can load any arbitrary ELF file as a software PLC, which is crazy. It shouldn't be this way. And it kind of looks like a backdoor in the code. Let's take a look. Here on the bottom, we can see the if clause, which loads the encrypted software PLC file. It just checks for a specific magic number at the beginning of the file, magic string. But here on the top, we can see the vulnerable if clause, which enables any ELF file to be loaded. Just checks for the ELF magic string at the beginning. This if clause shouldn't be here. And let's take a visual look at this. Any admin user on the Windows operating system can easily replace the original software PLC file with the modified version using the drag and drop method we showed you at the beginning. And when the PLC reboots, the hypervisor will load the modified version without checking for authenticity. And this undermines one of the key advantages of virtualization, which is isolation. This can be done remotely if an attacker gains admin privileges to the Windows operating system, and the changes are persistent, so it will withstand a power outage. Now, as a side note, we own the PLC that we were researching, so obviously we had an admin user which we could use to run all the experiments we needed that required admin privileges. And that's how we gained the first point of our game, which is very exciting. It was the first vulnerability we found, and we were ready to continue. And now that we could exploit this vulnerability and we can modify the software PLC to our liking, what should we make it do? So I like money. I wanted to make it mine Bitcoin. Eyal's a little more ethical than me. He wanted to modify it so he can better understand its internal logic. Unfortunately, we went with his approach. And to better understand how the software PLC works during runtime, we needed basic runtime information, like its registers and stack. But how could we do it? So what we did is we began with a very, very naive and simple approach, and we continued to improve and build on top of it throughout our research process. So remember that earlier we showed you that the Debug7 team was able to easily generate a crash dump by injecting an int3 command into the hypervisor? What if if we could do the same to the software PLC? What if by simply injecting an int3 command into its code, we could generate a crash dump? That way, we'll see its registers instead. But obviously, this didn't work. It was just too easy. It always has to be hard. But it was a good starting point to build on top of. And we looked for ways to improve this approach. As a reminder, the hypervisor launches the software PLC, and during runtime, control is shifted back and forth between them. There are many context switches. And we started to ask ourselves, what does an int3 command actually do when it executes in the software PLC? The previous slide, we thought it generates a crash dump. But obviously, that was wrong. But after a lot of research, we actually discovered that it shifts control back to the hypervisor. And that's when we asked ourselves the following fundamental question. Can we leak software PLC runtime information to the hypervisor's crash dump? And here's a visual explanation. While running within the software PLC, we'll shift control back to the hypervisor using an int3 command. And after the context switch, the hypervisor's registers will be identical to the software PLC's registers. And this is because the hypervisor is a bare metal hypervisor, which means that it shares its physical registers with all of its guest operating systems. Afterwards, we'll crash the hypervisor using another int3 command. And the registers in the crash dump will be identical to the software PLC's registers. And that's how we found a cool way to actually leak runtime information from the software PLC to the hypervisor's crash dump. And let's actually take a deep dive into the code we injected to make this happen. So let's begin by looking at a snippet of code of the software PLC. When looking at this code, we asked ourselves, what function is called here? Which basically means, what's the value of RAX? And nobody here knows what it is because it's only determined during runtime, so we couldn't really follow the flow of the code. What we could do is inject these commands. Deadbeef is a magic number we chose to tell the hypervisor that it's actually time to crash. And int3 shifts control back to the hypervisor, like we explained earlier. And after int3 executes and control is shifted back to the hypervisor, we end up on this line of code. And this is the code that we injected. Basically, what we do is we first check if edx is equal to deadbeef, the same deadbeef we placed in it earlier. And if so, we'll crash the hypervisor using another int3 command. But otherwise, we'll just resume the normal flow. And that's how we actually discover the value of RAX in the crash dump, as we can see here on the left. Now, this was a tremendous, tremendous breakthrough for us, because for the first time in our research process, and probably in all of the research process of this software PLC, we could actually see what goes on inside during runtime. And up until this point, all we could do was statically reverse engineer the assembly code. But it was very, very frustrating because for some reason, it stopped working at some parts of the code. Like it worked here, worked there, in random places it stopped working. So we tried to actually pinpoint the point of failure, see where this stopped working. And using binary search, we attempted to crash the software PLC until we actually found the point of failure. And the point of failure turned out to be this lidt command, which modifies the IDT, the interrupt descriptor table. What is this IDT anyways? It's a kernel structure pointed to by the IDTR register. And each entry points to a different interrupt handler. So in our case, when int3 is executed, the int3 handler shifts control from the software PLC back to the hypervisor. But if the IDT is changed and the handler is changed, it can prevent control from shifting back. So we overcame this by replacing the int3 instruction with the VM call instruction. Basically, VM call does the same. It shifts control back to the hypervisor, but without going through the IDT. So before, our breakpoint used to look like this, like in the example we showed you, but we changed it to use VM call instead of int3. And that's how we gained another point in our game and actually leveled up. And we were ready to continue to the next part of our research. But just before we continue, let's do a quick recap of what we managed to do up until this point. So first, via a vulnerability in the hypervisor that we found, we were able to easily modify the software PLC using the drag and drop method we showed you in the beginning. And by modifying the hypervisor and software PLC, we were able to leak runtime information from the software PLC. And this expedited the next part of our research a lot. Now I'll be handing the mic over to Rob to explain how we leverage this.
Thank you. So you might be wondering, how did this runtime information actually expedite our research? So during our research, we found out that static analysis can't always be enough. For instance, at one point, we wanted to see which files we opened during runtime. So we did use static analysis in order to find the obfuscated syscall table and map out several of its functions. But it was still hard to see which files were always opened only through the assembly code. So what we did is hook the open syscall such that the file name will be copied to the registers and then a crash dump will be initiated. So as you can see in the example here, this file name is ASCII encoded and saved in the registers in the picture. And that's how we could extract the file name that was opened. So for future researchers, here's the obfuscated syscall table that we found with several of the functions that we mapped out. Now these were really tough times because each of these crashes took about 5 to 6 minutes to reproduce. They were extremely error-prone and very tedious, but they were crucial for allowing us to debug our debugger as we built it. So now we'll get into the actual implementation of our debugger. Now, in order to build a debugger, we need a couple of things. First of all, we need to be able to send debug commands to the software PLC, and then we also need to be able to get debug information from the software PLC. Now, a lot of you might be thinking, this sounds a lot like a C2 server, and you'd be right. And that's exactly what we're going to do. We're going to build a C2 server. So that leads us to level 2 of our game, which is breaching the vault, or injecting data to the software PLC. So like most people, we do our best to avoid hard work. But developing a C2 server is extremely hard. It would require a lot more research and development, like finding more syscalls in the syscall table. But what if I told you that the PLC comes with a C2 server pre-installed? That would save us a lot of development time, and it even comes with a nice GUI. So let me introduce you to the PLC's web server. Now, the PLC exposes a web server via the software PLC, and this makes a lot of sense and has legitimate purposes. For instance, a technician can connect to it via his cell phone during maintenance. But how can we use this in order to inject data to the software PLC? So we'll show you. Here on the top, we have our web client, and on the bottom, we have the PLC. Now, the web client can request any file from the web server, including non-existing pages. For instance, dbg7 hello, which obviously isn't a real file. But when that request gets sent to the web server will attempt to open this so-called file. And when that happens, that will hit our open hook. So our open hook will check if the so-called file name starts with a dbg7 prefix. And if so, we will save it in the memory for later use. And otherwise, we'll just continue with the normal open flow and retain its original functionality. So this might have seemed easy, but we just gained a point and leveled up. And for the first time ever, we could now inject data to the software PLC. And we're basically halfway through implementing our C2 server. Which leads us to level 3, escaping the bank without getting caught, or exfiltrating data from the software PLC. So once again, we have our web client on the top and the PLC on the bottom. Now, the web client in this case will request the home page, which is a legitimate page. And when this happens, several CSS files will be read as well. And that's where our hook on the read syscall will come into action. Our hook will check if the file that's being read is the miniweb CSS file. And if so, instead of returning its original contents, we'll return the data that we saved earlier into the memory. And then, after that happens, this modified CSS file will be sent to the web client. And just like before, if it isn't the miniweb CSS file, we'll just return its original contents in order to retain the original functionality. So here are the results. On the left, we can see that the miniweb CSS file is open in the browser, And on the right, we can see its contents, which is dbg7 hello, which obviously isn't its original contents. So we just leveled up, and we got an extra point. And we just built a C2 server for the PLC. But we're not done yet, because we need to finish the final level of the game, which is defeating the boss. We need to build our debugger. So now we'll get into the implementation. So first of all, in order to build the debugger, we need to be able to add our own code and data without interrupting the normal flow. So here is the basic layout of any L file, or most L files, including the software PLC's L file. And what we did is add a whole new malicious section to it. We called that section hooks, and we gave it read, write, and execute privileges. So now we could add our own code and data and manage our own memory during runtime. We also wanted to give write privileges to the text section so that we could add a breakpoint during runtime. But lucky for us, the text section was already writable, which obviously is a huge security flaw. So now we'll get into the implementation and the architecture of the debugger. So once again, we have the web client on the top and the PLC on the bottom. Now, this time, the web client will request this funky-looking file name, which obviously isn't a real file. It's a debug command. And when this debug command gets sent to the PLC, it will hit our open hook. And our open hook will take this debug command and send it over to our command parser. The command parser will identify that this is a debug string, that this is a debug command thanks to the dbg7 prefix. It will identify the type of the command thanks to the types character, which in this case is a capital R, indicating a read string command. Now, the read string command has only one parameter, the address from which to read the string. So now, thanks to the type, the appropriate handler will be invoked with the parameters. And in this case, the read handler will read the string from that address and save it into the new section that we added for later use. And then after this happens, the web client will request the home page, and just like earlier, we will leak that information through the CSS file to the web client. So that's basically how our debugger works. The write handler operates in a very similar fashion to the read handler, and the breakpoint handler simply copies all the registers and any other information that you'd want to the CSS file, sends it to the web client, and then continues with the normal flow. So now we'll show you a video demonstration of our debugger. So here is the PLC's web server. On the left, we can see that the MiniWeb CSS file is selected, and on the right, we can see its contents. Right now it's empty because we didn't write anything to our memory yet. Now we'll go to our second tab, where we'll enter our commands. We will start with the read string command that we can see in the URL. We can see that the type is R, indicating a read string command. This command has one parameter, the address from which to read the string. Now we'll go back to the web server, refresh the page, check the contents of MiniWeb CSS, and see that test string appears, just like it does in the software PLC. Back to our commands tab, we'll run a write string command. This time, we're going to overwrite the previous string with pwned. After this, we will reread the previous string and go back to the home page. Now, after we refresh the home page, we can see that it's pwned. Now we will enter a breakpoint command. We can see that the type is indicated by the letter B and that we entered the breakpoint's address. Now we will run the software PLC so that a breakpoint will be hit. We will reach the home page and we can see of all the registers and that the PLC continued with flow. So the audio got cut out a bit in the end, but we just refreshed the home page and we can see that all the data in the registers appear in the MiniWeb CSS file. I'll go back to the presentation. So finally, after a lot of work and a lot of effort, and as you can see, a little bit of shooting, we finally defeated the boss. And we won our little game here. And we finally developed our debugger. But this little game has real implications on the real world. And this must be mitigated. So what can be done in order to mitigate what we showed you here today? So first of all, just some common good practice security mitigations should be instated, such as using an ASLR and not allowing the text section to be writable. Additionally, the hypervisor should be an ironclad wall between the two guest operating systems. Yet Siemens gave us an elegant backdoor that allowed us to modify the software PLC via the Windows operating system. This so-called feature must be removed. And as a matter of fact, Siemens did attempt to remove it. What they did is release a new version of the hypervisor that doesn't allow any unencrypted ELF file to run as the software PLC, but rather only encrypted ones. But the only problem is that we can use the same drag and drop method we showed you earlier to perform a downgrade attack on the hypervisor and use the hypervisor that we used in the example here, which means that effectively, this doesn't really stop any attacker. Which leads us to our next point. There must be a secure boot chain, because a secure boot chain is the only real way to prevent from a firmware modification attack on the PLC. So what is the impact for future researchers? So you may not have noticed, but we just entered a whole new age of PLC research. And for the first time ever, the software PLC can be dynamically debugged, and researchers can thoroughly examine and investigate the software PLC's firmware. But that's not all. Because all of Siemens' Simatic S7 product line share most of their code, which means that all of Siemens' latest and newest PLCs are now much more vulnerable. And what is the security impact of what we showed you here? So we showed you how a persistent Trojan horse could be developed for one of the leading PLCs in the market. This malware is persistent, it can withstand a reboot, and it can't easily be detected. And we know for a fact that bad actors, such as the actors in the Triton attack, have been seeking these kinds of capabilities, and we now know that it's possible. The longer the industry fails to properly secure PLCs, the greater the risk. There are already many PLCs out in the wild that are vulnerable to what we showed you here today, but they can't be updated since they operate critical infrastructure and they can't afford any downtime. So you might want to ask yourselves, how safe do you really feel? You shouldn't feel safe. What you should do is demand secure products and ensure that our modern world stays safe and secure. Thank you all for your time, and if you have any further questions, please feel free to contact us or step right up to the microphone.
Thank you for the information. So critical, as you said, S7 PLC being worldwide and so much critical plants being PLC being used. One question here, this when you mentioned this secure boot chain, is it a firmware integrity check? If it were done in the beginning, this would have made difficult for you to extract that content?
I'm not sure if I understood it fully.
The firmware integrity check during boot time.
So now there isn't a secure boot.
Yes, the secure boot is there now?
No, there isn't a secure boot.
Okay. Because usually when this kind of PLCs are intelligent devices, during in the booting, the firm, at least if not a secure boot, at least they will, the firmware integrity check they will do, the code signing and the firmware code signing, and then check the code sign before booting. Maybe it's not there now. That's why you were able to crack that, you were able to put that dummy code in the malware. The second thing is, have you got any CVE for this? You published this thing and got CVE?
So we did contact Siemens, and they did patch the hypervisor like we said. Like Eyal also said, it doesn't really fix it. I'm still not sure if there's a CVE. We're waiting for them to get back to us on that.
Okay. Now, usually the responsibility of the like researchers like you to publicly apply for an CVEs and get a CVEs from Mitre, then tell to the vendor saying that, okay, we all publish the CVE. It would help the industry, like they will get to know, because once the CVEs are there, it's published NVDs, at least the customers will get to know, okay, there are new CVEs have come in the PLC that create awareness in the public world.
We did go through a responsible disclosure process.
Yeah.
I'm just not sure yet if a CVE has been
Thank you. Yeah.
published.
Hi, thank you. Interesting, very interesting work, frightening work. So what's the current state of affairs and what is your policy with respect to the tool you have done? So is it now available to external researchers? And how long do you think Siemens would reasonably take in order to do anything to secure their S7?
So we won't be publishing our tool because we think that it might be dangerous right now to send it out to the world.
Okay.
And regarding Siemens, I think you should ask your questions directly to them. They'll probably know better than us.
No, but you said in your last slide that we have opened a new era where it's going to be available to all the researchers to blah, blah, blah. But
So-
if the tool is not available,
So
there
the
is no
tool-
new era, right?
So the tool isn't available, but we believe that people can develop it. We don't want to give it just like out to everyone. We want to show, like we want to make PLCs safer, so we did publish our research. But we still don't want to give the tool right out to everyone because that would still be dangerous.
Right.
You could still probably develop it. We showed you.
You have just shown to those who have the right resources that it's possible, just do it this way, in particular the people behind Triton, right?
Yeah, but we also showed it to Siemens and trust them.
Oh, it's fine. I mean, I'm not taking position here. I'm just asking what is yours?
As a policy of our research lab, it really depends, but as a general policy, we don't release code. Yes, like you said, we know that it can be easily reproduced. So I think it's kind of like a balance of actually displaying this research so action can be taken, because if nobody knows about this, it won't be fixed because it's really hard to fix. It's really hard to patch this kind of bug. Even if a secure boot chain is initiated and developed for future PLCs, I don't really see how this can be updated in current PLCs in the wild because it requires physical access to the PLCs and like installing, the keys and everything. But still, yeah, I believe in this research, so at least people know what they're at, because maybe some of this attacks already exist in the wild, and it's better to know it.
No. Okay. Thank you.
Okay, thank you, everybody.